Welcome to today's paper reading. Today's paper is titled, SparseGPT, Massive Language Models Can Be Accurately Pruned in One Shot. This paper was published on AR14 by Elias, Frantar and Dan Alistarh from the Institute of Science and Technology, Austria and NeuroMagic Inc. The abstract outlines the primary objective of the research, which is to investigate problem X with a focus on Y, aiming to advance the field of Z. The methodology involves analyzing data from A, using model B, and evaluating the results with C. The findings of the study identify key factors D, show a correlation E, and propose a solution F. SparseGPT is the first accurate one-shot pruning method designed to work efficiently on models with 10 to 100 billion parameters. It achieves this by reducing the pruning problem to a set of large-scale sparse regression instances. The method can induce 50 to 60% sparsity in models like OPT-175B and BLOOM-176B with minimal accuracy loss, and it can be executed on these models in under 4.5 hours. A key finding is that larger models are more compressible, dropping significantly less accuracy at a fixed sparsity compared to smaller models. SparseGPT also allows for the combination of sparsity with weight quantization techniques. Notably, the method is entirely local, relying on weight updates that preserve the input-output relationship for each layer without requiring global gradient information. Figure 1 illustrates the comparison between SparseGPT and magnitude pruning in terms of sparsity versus perplexity on the OPT-175B model. SparseGPT demonstrates the ability to induce up to 60% sparsity with only minor accuracy loss, as measured by perplexity. In contrast, magnitude pruning can only achieve a maximum of 10% sparsity before significant accuracy loss occurs. This highlights the superior performance of SparseGPT in maintaining model accuracy at higher levels of sparsity. Figure 2 illustrates the relationship between perplexity and model size across different sparsity patterns when using SparseGPT to compress the entire OPT model family. The OPT model family ranges from 135 million parameters to 175 billion parameters. The sparsity patterns examined include 50% unstructured sparsity, 4:8 semi-structured sparsity, and 2:4 semi-structured sparsity. The results show how SparseGPT effectively compresses these models while maintaining performance, with larger models demonstrating greater compressibility without significant accuracy loss. In post-training model compression, the task is typically broken down into layer-wise subproblems. The quality of these subproblems is assessed using the SID 96-2 error between the outputs of the uncompressed and compressed layers. The final compressed model is created by combining these individually compressed layers. For layer-wise pruning, the goal is to find a sparsity mask and possibly updated weights that minimize the error. This problem is known to be NP-hard, making exact solutions impractical for larger layers. A common approach is to separate the problem into mask selection and weight reconstruction. The mask is chosen based on a saliency criterion, such as weight magnitude, and then the remaining weights are optimized. Once the mask is fixed, the problem simplifies to a linear squared error problem, which is easily optimized. SparseGPT is an algorithm designed for accurately pruning large language models in a single pass. It achieves this by efficiently reusing Hessians across different rows, which is crucial for maintaining model accuracy while reducing computational complexity. The algorithm includes features such as fast approximate reconstruction, adaptive mask selection, and the ability to perform joint sparsity and quantization. This results in a computational complexity of OD3 hidden, making it practical for extremely large models, providing a full hidden factor speedup over exact reconstruction methods. Figure 3 illustrates the row Hessian challenge in the context of sparsity. Each row in the model is sparsified independently, with pruned weights indicated in white. This independence in sparsification leads to different row masks μ, which complicates the process of reconstructing the unpruned weights. The figure highlights the need for a method that can handle these varying masks efficiently while maintaining model accuracy. Figure 4 provides a detailed visualization of the SparseGPT reconstruction algorithm. On the left, it illustrates how, given a fixed pruning mask M, weights in each column of the weight matrix W are incrementally pruned using a sequence of Hessian inverses, HUJ-1. The algorithm updates the weights in the rows to the right of the column being processed, with pruned weights, dark blue, undergoing error compensation, while unpruned weights, light blue, remain unchanged. On the right, the figure shows the process of adaptive mask selection through iterative blocking, which helps in dynamically choosing the pruning mask during reconstruction. Table 1 presents the perplexity results of OPT models on the raw Wikitext2 dataset. The table compares the performance of dense, magnitude, prune, and SparseGPT methods across different model sizes and sparsity levels. The results show that SparseGPT consistently outperforms other methods, especially at higher sparsity levels, indicating its effectiveness in maintaining model accuracy while reducing the number of parameters. The experiments were conducted on an NVIDIA A100 GPU with 80 GB of memory, allowing the 175 billion parameter models to be fully sparsified in approximately 4 hours. The calibration data consisted of 128/2048 token segments from the C4 dataset, ensuring zero-shot conditions. The primary metrics used for evaluation were perplexity and zero-shot accuracy, focusing on models like OPT and BLOOM. Comparisons were made against the standard magnitude pruning baseline and prune, highlighting SparseGPT's efficiency and accuracy. Figure 5 illustrates the results of uniform pruning on the BLOOM-176B model. The figure compares the performance of SparseGPT and magnitude pruning methods. Notably, SparseGPT achieves up to 50% sparsity with minimal perplexity degradation, demonstrating a significant improvement over magnitude pruning, which collapses at lower levels of sparsity. This highlights the effectiveness of SparseGPT in maintaining model accuracy while significantly reducing the number of weights. Figure 6 illustrates the comparison between joint 50% sparsity combined with 4-bit quantization and size-equivalent 3-bit quantization on the OPT family of models with 2.7 billion parameters or more. The graph shows the perplexity on the raw Wikitext2 dataset for different models. It highlights that 50% sparsity with 4-bit quantization models maintain higher accuracy compared to their 3-bit counterparts, particularly for larger models such as the 175B parameter model, where the perplexity is lower at 8.29 versus 8.68 for 3-bit quantization. This suggests that the combination of sparsity and quantization can effectively balance computational efficiency and model accuracy. Figure 7 presents the sensitivity results for partial 2:4 pruning in large language models. The data reveals that later layers of the model are more sensitive to pruning than earlier layers. Specifically, skipping the last third of the model results in the best accuracy. This finding has practical implications for the SparseGPT method, which can sequentially generate increasingly pruned models by combining the first X layers from a SparseGPT run with the last layers X of the original model. This approach allows for a sequence of models with varying degrees of sparsity, each maintaining high accuracy. Table 2 presents the zero-shot results on various datasets for sparsified variants of the OPT-175B model. The table highlights the accuracy differences between the dense model and SparseGPT variants. Notably, magnitude-pruned models exhibit a significant accuracy collapse across all scales, contrasting with the stable performance of SparseGPT models. Additionally, SparseGPT demonstrates higher accuracy at the 2:4 sparsity level compared to the dense model, despite the more constrained sparsity pattern. These results underscore the effectiveness of SparseGPT in maintaining model performance under high sparsity conditions. In the realm of pruning methods, most existing techniques necessitate extensive retraining to recover accuracy, which is impractical for GPT-scale models due to their massive computational requirements. SparseGPT, however, is a post-training method that avoids this fine-tuning step. On the topic of post-training quantization, significant work has been done on quantizing OpenGPT-scale models, with methods like ZeroQuant and LLM.int8, demonstrating the feasibility of 8-bit quantization for weights, though activation quantization remains difficult. SparseGPT has been shown to be compatible with GPTQ, the state-of-the-art algorithm for weight quantization, and can be integrated with joint activation and weight quantization methods, leveraging efficient GPU kernels for performance improvements. SparseGPT is a method specifically designed for the GPT family of massive language models. It enables one-shot weight pruning without the need for retraining. The results indicate that models like OPT-175B and BLOOM-176B can achieve high sparsity levels of 50 to 60%, reducing over 100 billion weights, with minimal loss in accuracy, as measured by perplexity and zero-shot performance. This approach allows for the direct identification of sparse, accurate models near the dense model's performance, without relying on gradient information. Notably, larger models are found to be easier to sparsify. At fixed sparsity levels, the accuracy drop decreases with increasing model size. This suggests that inducing 50% sparsity results in practically no accuracy decrease for the largest models, which is highly encouraging for future efforts in compressing such massive models. This research was supported by the Horizon 2020 program under Grant Agreement number 805223, specifically for the ScaleML project. Additionally, the authors acknowledge the experimental support provided by Eldar Kurtic and the IST Austria IT department, particularly Stefano Elefante, Andrei Hornoy, and Alois Schlogel. Thank you for watching.